Let us look at proposition number 17. And in this proposition, there is a lemma before the proposition. So let's look at the lemma first. The lemma says, if to any straight line there is applied a parallelogram but falling short by a square, then the applied parallelogram equals the rectangle contained by the segments of the straight line resulting from the application. Let's see what this means. So here we are given a straight line and we have to apply a parallelogram such that there is a square remaining. So let's mark a point here. I have actually gone through the various steps in building this parallelogram, so I'm ignoring those steps. So we have a parallelogram on AB such that there is a square left. Okay, now let's look at what the lemma means. We are given a straight line AB. AD is the parallelogram applied to the straight line falling short by a square BD. So which means AD, this rectangle, is equal to AC by CD. You can look at it as the area of this parallelogram. So AC by CD. Now we know BC is equal to CD because this is a square. So which means we can write it as AD is equal to AC times BC. So what does this basically lemma do? It allows us to factor AB into two parts or find two factors of AB. So one of the factors is AC and the other factor is CD. So that is the lemma. Now let's look at the proposition. Proposition says, if there are two unequal straight lines and to the greater there is applied a parallelogram equal to the fourth part of the less minus a square figure, and if it divides it into parts commensurable in length, then the square on the greater is greater than the square on the less by the square on a straight line commensurable with the greater. And if the square on the greater is greater than the square on the less by the square on a straight line commensurable with the greater, and if there is applied to the greater a parallelogram equal to the fourth part of the square on the less minus a square figure, then it divides it into parts commensurable in length. So let's actually start developing this and see where it goes. So here, given two unequal straight lines A and BC, and BC is greater than A, we have to apply a parallelogram BD by DC, yes, with a square remainder. And this is where we are using the lemma. This is the square and this is the parallelogram which we have applied. And this is equal to the fourth part of this square on A. This is the fourth part and this is the full square on A. So as you can see, it is the fourth part. And we can get this fourth part by actually taking half the length of A. Such that, now this parallelogram should be such that BD, this is D by the way, BD by DC. Now when I say BD by DC, we are talking of this parallelogram, BD by DC. So this one. So BD by DC is equal to fourth part of A square or square on A. Let BD be commensurable in length with CD, and let me actually put the square on BC also. BC square is greater than A square by a square on a straight line commensurable with BC. So since BC is greater than A, BC square will be greater than A square by a square on a straight line commensurable with, so BC square is greater than A square on a straight line commensurable with BC. Now we bisect BC at E. So BC we bisect it. So let's bisect it. To mark a point on this side of E, let's say F, such that EF is equal to ED. So we know how to do this. Draw a circle of radius ED. Take the intersection point, and now we can hide the circle. So now here EF is equal to ED. EF is equal to ED means BF is equal to CD. BF is equal to CD. Now how? Just try to figure it out. E is the midpoint. So we have one part of EC, that is ED. Now this part is equal to this part. So naturally, which means BF will be equal to DC. BC is cut into equal parts at E and into unequal parts at D. So basically, we have a proposition long time back we saw in book 2. If this is the situation, the proposition says BD by DC plus ED square is equal to EC square. Now let's quadruple this. We multiply everything by 4. So 4 times BD by DC plus 4 times ED square equal to 4 times EC square. When we do that, what happens? Now BD by DC is equal to this parallelogram, or rather rectangle, and this rectangle is equal to this fourth part of the square on A, which means 4 times of this will be equal to A square, the square on A. ED square times 4. So the square on ED and the square on FD. What will be the relation? So if this is the square, so ED square will be, if we multiply it by 4, we will get this green square. And that's green square is DF square is equal to 4 times EC square. EC square. Again, this is half. This is the midpoint. So this will be this square, and 4 times this will be the square on BC. So that means A square plus DF square is equal to BC square. Or in other words, BC square is greater than A square by DF square. BD is commensurable in length with CD. We started with that. BD be commensurable in length with CD. BC, which means BC is also commensurable in length with CD. BD is commensurable in length with CD. That means BC is also commensurable. BC, which is the sum of BD and CD. That will also, sum will be commensurable with the part, if the parts are commensurable. CD is commensurable with itself, of course, and BF. Why? Because BF is equal to CD. We saw here BF equal to CD. So CD is commensurable with itself and with BF, which is equal to CD. So here, if you notice, BC is commensurable with CD, CD is commensurable with CD and BF. That means BC is commensurable with CD and BF. So BC is commensurable with the remainder FD or DF, which means BC will also be commensurable with the remainder FD. BC square is greater than A square by DF square, which is nothing but the square on a straight line commensurable with BC, since FD is commensurable with BC. That is the first part of the proposition. Now let's look at the second part. Now here we start with this. BC square is greater than A square by a square on a straight line commensurable with BC. We do the same construction. Apply a parallelogram BD by DC with a square remainder. Follow the same steps. We end up with the same thing. That is BC square is greater than A square by DF square. We are given that BC square is greater than A square by a straight line commensurable with BC. So BC is commensurable with DF, which means BC is commensurable with BF plus DC. Because BF plus DC is the remainder if we remove DF from BC. But BF plus DC is commensurable with DC because BF is equal to DC. So their sum will be 2DC. So 2DC is commensurable with DC, which means BC is commensurable with DC. Taken separately, BD is commensurable with, taken separately means BC is commensurable with DC. So taken separately means BD is commensurable with DC. Now see here, in the first part, we started with BDB commensurable in length with CD and we proved this, that BC square is greater than A square by A square on a straight line commensurable with BC. And in the second part, we started with the conclusion of the previous part and we arrived at the starting. That is proposition number 17 of book 10 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.